Sup, it's David Praise, and in today's tutorial, you're going to receive a gentle introduction to training your first emotion detection system using the PyTorch Deep Learning library. And then this network will be coupled with the face recognition network that OpenCV provides for us, so that we can successfully execute our emotion detection in real time. So today's tutorial is actually part 1 in our 2 series of building our emotion detection system using PyTorch. So first, we're going to train an emotion detection system from scratch using PyTorch, and then in the next tutorial, we're going to build a real-time emotion detection system using PyTorch and OpenCV. So let's get started. So you might ask a question: can computers actually do a better job than us in accessing our emotion states? So I designed a neural network that gives my computer the ability to make inference about the emotion states of different people coming to Novak situation. In simple words, basically just giving them the eyes to see and understand how we humans interpret different individuals' reactions to certain situations. So before starting this tutorial, it's important to be aware that our human emotions constantly change at every given second, as we can never be truly 100% happy or 100% sad. Rather, we show some kind of signs of mixed emotions together. So for example, when you're experiencing this situation based on different response to the situation concerning his band, people showed signs of being surprised or in fear, happy or sad, angry or neutral. So rather than simply assigning a single label to each video frame we are analyzing, it will be more reasonable to represent our results in form of probability values that we can later save and further study in much depth. So for this tutorial, we'll be utilizing the facial expression recognition 2013 dataset for this project. And according to the sources, this dataset was created by Goodfellow in their 2013 paper, Challenges in Representational Learning. And it's also great to know that the facial expression dataset, also called FAIR 2013, can be found on this Kaggle page, where you can download the dataset and start using it. And additionally, we should also be aware that the dataset consists of a 48 by 48 pixel grayscale image of faces with different expressions hidden behind each of them. And it's also crucial to be aware that these faces are more or less centered and are all resized to like a specific pixel size. And the major goal is to actually categorize each face based on the emotions that are shown in one of the 7 categories, which now has become 6 because we've combined anger and disgust, since there were only like a few samples within the disgust folder. So in order to successfully follow this tutorial, you need to have the prerequisite libraries installed in your system, such as like PyTorch, OpenCV, Matplotlib, scikit-learn, and other more packages that you will find on the blog posts. And you will need to have them installed either in your system or your virtual environment, which are recommended. And the good thing is that you don't have to worry too much about like OpenCV, scikit-learn, or the other libraries that are needed, because I've already covered them in the tutorial, which you can see on the screen right now. And this is mostly for Linux users, as they can easily like pip install them and they're ready to go. However, if you're configuring your development environment for PyTorch specifically, I recommend that you adhere to the instruction guide that is on their website. And trust me when I say it's very easy to install and you're ready to go. So let me show you how to do that. So in order to install PyTorch, all you need to do is just type in the URL pytorch.org and then click on install, scroll down and just select your preference. So if you're on a Windows machine, just click stable, Windows, pip, Python, and then choose your compute platform. So we'll be using CUDA 11.3. So you just copy this command. Make sure that you've activated your virtual environment. Paste the command that you've copied and just click the enter button. And you just have to wait for the installation to complete. So once you're done installing all the necessary libraries, let's move on to reviewing our project directories. So in this tutorial, we have like 5 Python scripts that we're going to review. So first we have our EmotionNet, which is our Python implementation of our custom EmotionNet architecture. And then we have our config.py script, which stores the network hyperparameters and the path to our files. So inside our utils.py, this just contains additional methods that will help prevent our network from overfitting while training. And inside our init.py, this just let the Python interpreter just know that this directory here contains code for our Python module and also acts as a constructor for the Neuraspike package. And then finally, we have our train.py script, which just actually trains the model on the FER 2013 dataset using PyTorch, then just serialize the train model to our disk, which is just model.pth and as well as plot.png, which just contains our training history and loss during the training procedure. So inside our model directory, here we have our deep learning based phase detector architecture, which is this file over here. And then we have our cafe model weights, which is this file over here. With our project directory reviewed, now let's move forward to training our custom EmotionNet detector using PyTorch. All right, so let's have a look at what's going on within our config script. So over here, we had OS imported. Then we just initialize the path to where our root folder is, which is dataset, as you can see over here. And then we just initialize the path to where our train datasets are located, and as well as also where our test datasets are also located. And then we just initialize the amount of samples that we're going to use for training. So we're going to be using 90% for training and 10% for validation. And the reason why we have the split is because since we don't have any validation samples already existing, we'll define our split percentage to use relatively 90% of our trained dataset for training the model and the remaining 10% from our trained dataset in order to validate the model to see how it's performing while training. And then we just, specify the batch size, the total number of epochs, as well as our initial learning rate. So now that we've seen what's happening in our config file, let's actually move to our emotion network that we've created. So when I was working on this project, I tried a couple of networks like the ResNet 18, ResNet 34, and to my surprise, I wasn't really getting a really good result because I tend to notice that my model started overfitting, which is definitely a bad sign because it won't be able to generalize on our real world application. So what I did next was that I started looking into different models. I also had to try a more simpler model like VGG 19, then I moved to VGG 16. I wasn't getting something interesting. And when I used the VGG 13 network, I started noticing quite a bit of some improvements. So what happened then was I started messing around with the fully connected layers and I was actually getting a bit much better results. Then I moved forward into actually just modifying the activation functions that we use. So from a relay activation function into an ELO activation function. And I was actually getting something really, really good. And I can actually show you the results. You could see how the validation loss, which is the black line, how it's decreasing over time, as well as also the training loss. So which is good. So it tells us that our model is actually learning something. So just to walk you through what's happening here, I just imported our necessary packages, defined a class called emotion network, and then inherit all the properties from the torch.nn. So it's PyTorch neural network package. And over here is just a configuration for the network. Then inside of the init function, it receives actually two arguments, which first is the number of channels. So since we're working on the grayscale image, this is actually going to be set to 1, and you see that later. And the number of classes, so which we have over here defined. So you can see that we have already 6 labels. So within our init function, we've defined some attributes over here, such as features. And what this does is that it makes a call to our make layer function that we've created. And what the make layer does is that it helps us build the convolutional layers of the VGG 13 network based on the configuration parameters that we specified over here. And our classifier attributes is just the fully connected layer that is followed by after our convolutional layer. So on this attribute, we only have two linear layers in total, and the first layer includes the elu activation function followed by the dropout function. So after the initialization, our network will really know how each layer is actually ordered. So in order for PyTorch to know what layer follows after another, we actually have to create this forward function. And over here, it receives as an input an image, which is actually passed into our convolution layer. And then on this line, it just flattens the output of the convolution layer, which is then being passed into our dropout layer and then served into our fully connected layer. And then finally, we have this make layers function, which receives as an input the image channel, so the number of channels. And since we're working with a grayscale image, it's actually going to be 1. And then the network configuration. So what happens over here is like we've initialized a list on where we're going to store the sequence of our network. So we just iterate over through our config. So this list that we've created over here. And if x is equals to m, that means just like include like a max pooling layer of a kernel size and stride of 2. Else, we're just going to append this block of a convolution layer followed by a batch normalization and then an elu activation function. And then we'll update the input channel after all these operations. And finally, we'll just return all the layers in a sequential manner. All right, so that's it for this script. All right, so now that we've seen our emotion net script, let's actually move into our utils.py script. And what this Python script does is that it just contains additional methods that just helps our network from overfitting while training. So over here, I've implemented like 2 callback functions, which just helps prevent our network from overfitting while training the model. And the 2 methods that I've actually implemented are the learning rate scheduler and the LA stapling technique. So you can as well go to the blog post to actually read more in details about what's going on. However, a general summary over here is that we all know that when you actually have some experience training deep neural networks, you will know that some of the major issues when working with these models are, it could be that it tends to overfit very easily or might become difficult to train when you don't have sufficient amount of data sets. And secondly, it's usually like using a fixed learning rate, which is quite tricky to deal with. So what we've done over here is that we've implemented a learning rate scheduler. And what this does is that it dynamically decreases the learning rate while training. So from what I know, there are of course a few hacks on how to actually go about, decreasing the learning rate. However, the most common technique used is to just check if the validation loss doesn't improve after a certain number of epochs, or also as well noted as patience. So after like 5 epochs, if our validation loss isn't improving, what's going to happen is that we're actually going to decrease the learning rate by like a factor. So our new learning rate was going to be like the old learning rate, so the initial learning rate that we had, multiplied by a factor value over here. And over here, we've defined like our call method. And what this does is that it executes this class that we've created whenever the validation loss as an argument is actually supplied to the object of the learning rate scheduler class. So moving on, apart from the learning rate scheduler that we've already implemented, we also implemented the early stopping mechanism, which is also another technique that prevents our network from overfitting while training our model. And while training your model, you might have experienced a situation whereby your training or validation loss is actually starting to diverge. And this can happen because, your network is beginning to overfit, or the learning rate scheduler that you've implemented isn't helping the model to learn anymore. So the reason why we implemented this is just to easily break out of the training procedure if our validation loss doesn't improve over a certain number of iterations. And over here, I've defined our patience as 10. So what happens is that once we've decreased our learning rate and our network is not actually improving, what's going to happen is that we're easily just going to break the whole training procedure. And if you just like, look into the call function, whenever our validation loss as an argument is actually supplied to the object of the early stopping class that we've created, what's going to happen is that it's going to initialize the first validation loss as our best loss. And what happens over here is that at each iteration, we're going to compare our previous, validation loss with the current validation loss. And if it's less than min delta, and min delta over here is set to 0, so let's say our best loss, if it's like, let's say 1.6, and then our validation loss that we got, it's like, let's say 1.8, you can see that the difference between 1.6 and 1.8 is -2. So if -2 is less than 0, what's going to happen is that we're going to initiate this counter variable and we're going to keep incrementing it. So if our counter variable is greater than or equals to 10, what's going to happen is that we're going to initiate our early stopping mechanism, which just breaks the training procedure. However, if we notice our network is starting to improve, so let's say if we have like 1.6 over here and 1.4 over here, and if this is definitely greater than 0, we're just going to reset our counter and set our best loss to be this current loss. And then if we open our init.python file, what happens over here is that it just lets the Python interpreter just know that this directory over here contains code for the Python module, and it also acts as a constructor for the Neuraspike package that we've created over here. All right, so now that we've gone through our init file, now let's actually review our training script. So just to give you a general overview of what's happening in this script is that first, we're going to prepare our data loading pipeline. So a little piece of code that's going to help us read our own images from the directory. Then we're going to initialize our emotion network that we've actually built, which is inspired by the VG13, which is just a little tweak into it. And then we're gonna, initialize as well our training parameters. Then next, we're just gonna build our training and our validation loop. So after we finish training our model, then we'll be able to validate our model. And then we'll visualize, the training and validation loss and accuracy. And then finally, we're just gonna analyze our test samples with our trained model. So first, we started out by, importing all the necessary Python modules, layers, activation functions from PyTorch, which we're going to be using while training the model. And next, we just initialize our arc parser, which just, lets us parse command line arguments via the terminal. And then we just checked, if whether we're going to be using GPU or CPU while training the model. So if you have like GPU available on your computer, then the whole process is actually going to be run on your GPU. However, if you don't have GPU available, then this whole training process is actually going to be executed on your CPU. So next, we just defined like a pre-processing step that will be applied to each image. So while we're training, validating, and as well as testing our model. So while training our model, we're first going to apply this operation. First, convert an image into grayscale. Then we're also going to apply some data augmentation techniques like random horizontal flip, so to flip the image across the y-axis. And then we also perform like a random crop, so 48 by 48 pixel. And finally, we have to convert our image into tensor because PyTorch requires that all inputs should be in a format of tensors. And then this test transform is basically the transformation that we're going to apply to our validation samples as well as our test samples. So first, we're going to convert the image into grayscale and then into tensors. So over here, using the image folder, this is a very efficient tool that PyTorch has actually built for us. And what this does is that it helps us load our images from like a specific folder. So we don't have to like manually implement like going through the image, finding which image corresponds to which label. So PyTorch does a really great job in handling that. So you can see that we've applied our train transform to our train dataset and our test transform to our test dataset. So over here, we just extracted like, the classes that are available. So these are already the classes that you've seen: angry, fear, happy, neutral, sad, and surprise. And then we also just got the total length of the classes, which is 6. So remember I told you earlier that we don't have validation sets available, and we're going to use 10% of our trained samples for validating our model and the remaining 90% for actually training our model. So over here, we just got the total number of samples, and then we just, computed the size that we're going to use for training and the size we're going to use for validating our model. We printed this out on the terminal. And what the random split does is that it just randomly splits our training data set into training and validation sets by, the given lengths that we've actually specified over here. So moving on, after we randomly, split our data set into training and validation samples, we now went ahead to just modify the data transform that is actually applied towards our validation set. So initially, the validation set still has this transformation technique. So what this line over here does is that it just modifies the transform to this specific transformation. Right. So if you remember earlier that I told you that we're dealing with an imbalanced data set, what we actually did now in the following few lines is we just applied a technique called oversampling. And what this does is that it just creates new synthetic examples for just the minority classes. So what we've done over here is that our counter class, it just counts the number of samples are available in each class. And on this line over here, we just determine what weight should be applied to each and every single one of these categories. So over here, we just initialize like a placeholder for each target image. And what we've done is that we just iterated through our training data set just to get the weight for each class. So for example, so if our label is actually 1, what we're going to do is just, get the weight that corresponds to class 1 and then modify this sample weight placeholder that we've generated over here, modify the weight that corresponds to that specific image at that given moment. And then we just define our random sampler, which just, randomly samples the labels in our training data set. So over here, we just pass in our data sets into data loader. And what it does is that it helps return our loaded images. Remember, I told you that I already loaded the images using the image folder. What it does is that it just returns our loaded images in form of batches while either, training, validating, or evaluating our network. And also for the train data loader, we also specified the sampler, which is actually, the weighted random sampler that we've created over here. So over here, we just initialize our model. And as you remember, as for the number of channel, it's going to be 1 because we're expecting a grayscale image. And the number of classes, it's actually going to correspond to what we've already calculated over here. After we've, initialized our model, what we need to do is to just call this to device. And what this does is that it moves our model to either the GPU or the CPU. And over here, we initialize our optimizer and our loss function that we're going to be using. So for the optimizer, we're going to be using the stochastic gradient descent. And if you want to learn a bit more about the inner workings of this algorithm, I already wrote a tutorial for this, and I'll leave the link in the description below so that you can read more about this topic. So as for the parameters that we pass, we're going to input our model parameters. This is just basically the weights for our model. And then for the learning rate, it's going to be the initial learning rate that we've defined over here, which is 0.1. So back to our script. Now we initialize our loss function. So we're going to be using the cost entropy loss function, which is just a combination of a softmax and a negative log likelihood. So over here, we just initialize our learning rate scheduler and our early stopping mechanism. And over here, we just calculated how many times are we going to go through our training data and our validation data in a single epoch. So we could go through our training data in one epoch, let's say 3,000 times. And in our validation data set, it could be a bit smaller. So in order to actually, save our training history while training our model, I initialized a dictionary which stores the train accuracy, the train loss, as well as the validation accuracy and the validation loss. And over here, this is actually where the whole training process actually begins. So we just started our timer just to see and keep track of how long it actually took our model to train. Now we started by iterating through the number of epochs that was actually set within our configuration file, so which is like 50 epochs. And then what's going to happen over here is that we're going to set our model into train mode. And what this does is that it tells PyTorch that we actually want to update our gradients. So we actually, started out by, initializing this following variables. So our total train loss and total train validation loss. And this is like a variable that just, keeps track of our training loss and our validation loss in each iteration. And then our train correct and validation correct. And what this does is just keep tracks of the number of, correct predictions in this current iteration. And within this for loop, all that's happening over here is that we're just going through our data loader object that was already, created for us. And what this does is that Python automatically just, returns like a portion of your training data set. First move it to the device that you're going to use for training, either, CPU or GPU, and then perform like a forward pass and then, calculate, the training loss. And then after, we've performed like the forward propagation, this following step is like very, very crucial, especially when you're working with PyTorch. So, and they have to actually be, be using this following operation. So first we need to like, zero out the gradients that were accumulated from, previous iterations. And then we're gonna, perform back propagation before, updating our model parameters. So if you remember model optimizer.step, if you remember once we, initialize our optimizer as a parameter, we pass in our model weight. So what's gonna happen is that once we call optimizer.step, after we've performed the backward pass, then we're going to update our gradients using the stochastic gradient descent optimizer. So what's just happening over here is that we're just keeping track of like the loss, because remember that we're going to like, iterate through our train data loader this amount of time. So which is going to be like, the total length of our training data set, integer division with the number of batch size. So over here we have our prediction.argmax, which just gets the index that has like, the highest probability. And then we're going to compare it with our target variables. So for example, if we have like, let's say 2 over here and our target is actually 2, what we're going to do is like, we're going to check if 2 is actually equals to 2. So this is actually going to return either true or false. So what's happening over here is that we just converted our Boolean statement into a float. Then since, we're working with batches, we're going to sum the total number of like either ones or zeros, so true or false, and then just get the integer value. So instead of getting our result in form of a tensor, we're going to get our result in form of a numpy array. So after we've looped over all the batches in our train data set for this, current iteration, now we're gonna have to like, evaluate our model. So first we need to, set our model into evaluation mode to just tell PyTorch, okay, we're not gonna be updating any gradient. And also when we set our model into evaluation state, it actually disables the dropout and dropout layers that we've actually implemented when building our own network. So the same thing that happens when validating our model, it's quite similar to what we've seen while training our model, except with a few changes. So basically, we're not going to be, performing any sort of, we just wrap this whole operation within this with statement, which just, automatically turns off PyTorch autograd. So over here, we just, calculated the average training and validation loss. So basically, it's just, the total training loss that we've kept track of divided by, the training steps. So what we've actually computed over here. And as well as also our average validation loss. And also, we also calculated the accuracy. So basically the total number of correct samples that our model has gotten divided by the total number of data sets. And also as well as for our validation set. And, we just printed this out to our command line. And then we just saved our training and validation results in our history dictionary that we've created over here. All right, so over here is where we're actually gonna execute our learning rate scheduler and error stopping mechanism. So we need to get the validation loss, and we're gonna pass it as an input into our learning rate scheduler and as well as our early stopping technique. So if you remember, for our learning rate scheduler, after 5 iterations, if our validation loss is not decreasing, we're gonna start decreasing our learning rate so that we can actually reach our optimum goal. And for the early stopping technique, we're gonna just keep checking if our validation loss keeps increasing after 10 iterations. And if that condition holds, what's gonna happen is that we're just gonna check if early stop was actually enabled. And if it's true, then we're just gonna break out of our training procedure. All right, so once we're no longer within our loop, so we just subtracted our current time from our start time just to see how long it took our model to train. So over here, we just, moved our model back into CPU if it was actually, sent to the GPU. And we just saved our model's weight in this specific location, which you can see over here. And over here, we just, plot our training loss and accuracy over time, which is this plot that you can see over here. And then in order to evaluate our model, we're just gonna, put our model back into device. Then we're gonna turn off PyTorch's autograd and set our model back into evaluation state. Initialize like a list, which just keep tracks of the whole prediction. Then we iterate it through our test data set, pass the image into the current device that we're working on, and then we just infer our image through our model, get the index with the highest probability, and then populate this prediction list that we already initialized. And finally, to complete this train.python script, we just assessed our model's performance using the classification report from scikit-learn to provide us like a general overview of the model's prediction. Also, just to understand which class our model predicts well or worse compared to the other classes. So if we execute our model, so if you're using PyCharm, you can actually walk your way around this. So you can just, stop it over here. Just click edit config. And for the parameters, you're going to pass in these arguments. So we don't have to manually do it on the command line. So you can either run it that way or, just copy this command. Going to terminal, make sure you activate your virtual environment, then script activate, and then just copy this and paste it over here. All right, so now that our whole training process is actually running, we're just gonna wait until our training process is actually completed. All right, so now that our training process is actually completed, you can see that the early stopping mechanism was actually initiated, and which broke the training procedure. So when able to actually reach the 50th operation. So you can as well, see that it took our model 14 minutes to actually train. And while we evaluated our model, you can see that we got a general accuracy of 59%. You could as well, analyze the precision, the recall, and as well as the F1 score. All right, so that's it for this tutorial. And in the next tutorial, we're going to learn how to take our trained model and build an emotion detection system, which will help us understand how the top tennis players or individuals are reacting to Novak Djokovic's visa ban. So that's it for this tutorial. And if you've liked this video up until now, be sure to hit the like button. Don't forget to subscribe if you haven't already, and make sure you turn on all notifications so that you get an update on when next I post. And if you have any questions, feel free to type them down in the comment section below, and I will take my time to actually get back to you. And there's also a blog post for this video where you find a much detailed explanation on what's going on in each line, and also you will get the code from there. And I will leave the link to this blog post in the description below. Thank you for listening, and until then, see you next time.